Performance analysis and enhancement of marine propeller. Abstract. This analysis of a propeller is based off the coordinates of model KCD32, Emerson and Sinclair, 1967. Using SOLIDWORKS to recreate the geometry of a three-dimensional geometry, analysis was conducted. The study is completed using a computational program, Ansys FLUENT, and velocity, pressure distribution, torque is compared to experimental results. Reasonable results are produced such that the torque and efficiency trends will be in acceptable limits with respect to experimental data. The acquired results are used as input data to carry out stress analysis on propellers made of three composite materials, namely carbon composite, alumina composite and polymer composite. Keywords: hydroenergy, optimization, FSI interaction, blade design, CFD analysis, marine propeller, advance. Coefficient, torque, torque coefficient, material, convergence, etc. Introduction. A propeller is a type of fan that transmits power by converting rotational motion into thrust. A pressure difference is produced between the forward and rear surfaces of the aerofoil-shaped blade, and a fluid, such as air or water, is accelerated behind the blade. Propeller dynamics, like those of aircraft wings, can be modeled by either or both Bernoulli's principle and Newton's third law. A marine propeller of this type is sometimes colloquially known as a screw propeller or screw. However, there is a different class of propellers known as cycloidal propellers. They are characterized by the higher propulsive efficiency, averaging 0.72 compared to the screw propeller's average of 0.6, and the ability to throw thrust in any direction at any time. Their disadvantages are higher mechanical complexity and higher cost. 2. History of propeller. In 1835, two inventors in Britain, John Ericsson and Francis Pettit Smith, began working separately on the problem. Smith was first to take out a screw propeller patent on May 31, while Ericsson, a gifted Swedish engineer then working in Britain, filed his patent 6 weeks later. Smith quickly built a small model boat to test his invention, which Shashank P. Shet, Bachelor of Engineering student, Department of Mechanical Engineering, Shri L. R. Tiwari College of Engineering, Mira Road, Thane, Maharashtra, India. Dheeraj K. Amin, Bachelor of Engineering student, Department of Mechanical Engineering, Shri L. R. Tiwari College of Engineering, Mira Road, Thane, Maharashtra, India. Later at the Royal Adelaide Gallery of Practical Science in London, where it was seen by the Secretary of the Navy, Sir William Barrow. Having secured the patronage of a London banker named Wright, Smith then built a 30-foot, 6-horsepower canal boat of 6 tons burthen called the Francis Smith, which was fitted with a wooden propeller of his own design and demonstrated on the Paddington Canal from November 1836 to September 1837. By a fortuitous accident, the wooden propeller of 2 turns was damaged during a voyage in February 1837, and to Smith's surprise the broken propeller, which now consisted of only a single turn, doubled the boat's previous speed, from about 4 miles an hour to 8. Smith would subsequently file a revised patent in keeping with this accidental discovery. 3 objectives. To study different types of propeller. To perform extensive literature survey. To simulate experimental test in Emerson Paper 1, numerically using commercial software Ansys FLUENT 18.0. To study effect of change in material with composite material, in overall efficiency of marine propeller. 4. Problem definition. A propeller is the most common propulsor on ships, imparting momentum to a fluid which causes a force to act on the ship. The ideal efficiency of any size propeller, free tip, is that of an actuator disc in an ideal fluid. An actual marine propeller is made up of sections of helicoidal surfaces which act together screwing through the water, hence the common reference to marine propellers as screws. 3, 4, or 5 blades are most common in marine propellers, although designs which are intended to operate at reduced noise will have more blades. CFD study of propeller can be used study its different problem like propeller-induced vibration, tip erosion, propeller cavitation, singing propeller, etc. A good was demonstrated first on a pond at his Hendon farm, and CFD model of propellers working can be utilized to study cause of above problems and methods to prevent it. V methodology. A propeller is a type of fan that transmits power by converting rotational motion into thrust. In this project we have studied different types of propeller. After we have selected marine propeller for designing of 3D model. The modeling of marine propeller was done in SOLIDWORKS 2015 software. By using this software, time requires in producing the complex 3D model and risk involved in design and manufacturing process can be minimized. After modeling complex 3D model, it was further imported to the CFD analysis. The overall system of marine propeller is analyzed using CFD analysis. CFD study of propeller can be used study its different problem like propeller-induced vibration, tip erosion, propeller cavitation, singing propeller. After selection we have designed 3D model propeller of different shape and sizes using SOLIDWORKS software. This model was further used to develop CFD model to get effect of rotation of marine propeller at different advance coefficient values, J. The CFD data and different settings were used with reference to previous literature work used in research done on wind turbines. The results obtained from CFD analysis was transferred to static structural analysis as a part of one-way Fsi simulation. The pressure over blade surface was mapped to surface of marine propeller blade for loading boundary condition and blade was fixed at shaft. This process was performed on 4 different blades of different materials. This was performed to achieve proposed objective of reducing weight of blade, without affecting working of marine propeller. 6. Marine propeller specification. The coordinates of the blades were based on a 5-blade right-hand propeller, model KCD32, Emerson and Sinclair, 1967. The coordinates are set up as shown in figure 5.4.1. There are 7 sections, foils, at varying pitch and distance from the hub. 7. Computational fluid dynamics. Analysis. A mathematical model, governing equations. The governing equations are the continuity and Navier-Stokes equations. These equations are written in a frame of reference rotating with the blade. This has the advantage of making our simulation not require a moving mesh to account for the rotation of the blade. The equations that we will use look as follows: conservation of mass. Where is the relative velocity, the velocity viewed from the moving frame, and is the angular velocity. Note the additional terms for the Coriolis force and the centripetal acceleration, in the Navier-Stokes equations. In Fluent, we'll turn on the additional terms for a moving frame of reference. For more information about flows in a moving frame of reference, visit ANSI Help View Fluent Theory Guide 2. Flow in a moving frame of reference and ANSI Help Viewer Fluent Users Guide 9. Modeling flows with moving reference frames. We use the Reynolds averaged form of continuity and momentum and use the SSTK omega turbulence model to close the equation set. B. Boundary conditions. The input values from the experimental data, Emerson and Sinclair, 1967, have been converted to SI units. The values they have used have not been specific, as they tested a number of different shaped propellers and stated only cavitation number but not speed or pressure. However, they have given a rang E of 10 to 16 feet per second. For this project, a fixed linear, upstream, velocity was chosen, 13 feet per second, and the revolutions were varied in accordance with J. J equals V slash, N asterisk D. Where J is advance coefficient. V is velocity of fluid. N is rotation per SEC. D is diameter of marine propeller. The solver required an input of the angular velocity the propeller would be rotating at these values below. Diameter, m, linear velocity, m/s, j revolution, 1/s, angular velocity, rad/s. B. Blade velocity. Figure 4 blade velocity, scalar and vector. C. Pressure contour. From this plot, it is visible that the pressure is low on back surface of blade as compared to the front surface of blade, realized from color scheme. Red region shows positive pressures, green region shows same magnitude but negative in nature, while blue region indicates much higher negative pressure. Figure 7 comparison with experimental data. Fsi simulation. This section considers the deformation due to hydrodynamic loading of a marine propeller blade by performing a steady-state one-way Fsi, fluid structure interaction, analysis. Previous section of CFD analysis uses Ansys FLUENT to develop the hydrodynamic loading on the blade. In this section, the pressures on the wetted areas of the blade are passed as pressure loads to Ansys mechanical to determine stresses and deformations on the blade. A setup. Figure 8 Fsi Boundary Conditions. The water flows towards the negative x direction, into the page on the above diagram, at 3.9624 m/s, which is used in experimental procedure. This incoming flow makes the blade rotate at an angular velocity about the x-axis. We imported pressure over blade surface from CFD model we developed using system coupling. Note that to represent the blade being connected to a shaft. IJERT 9 IS 020020 www.ijert.org. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org. ISSN 2278-0181. Volume 9 Issue 02, February 2020. 11 Results and Conclusion. A. Results. From results, it can be concluded that polymer fiber-based composite material is best suitable replacement from commonly used material viz., alloy. It is also noted that weight is optimized. Table 1 Fsi results. B. Conclusion. Low-weight blade can be designed and manufactured with strong load-carrying capacity. Numerical simulation data of Emerson experimental test. Fluid structure interaction data in said experiment. Increase in efficiency of marine propeller on replacement with composite material by reducing its weight without compromising its strength. Optimized component helps in increasing performance of marine turbine. Acknowledgement. This work was supported by Department of Mechanical Engineering of Shri L. R. Tiwari College of Engineering, Mira Road, Thane, Maharashtra.